from Tsinghua University, and he's going to tell us about the multiple uses of thank you, of modular berry phases.
Okay.
So this is just like to say that this is like the first lecture of 3. So we're going to have like 2 today and 1 tomorrow. So, and there's going to be like a half an hour break in between the 2 lectures today. So Bartek, please.
All right. Thank you. Thank you very much for the invitation to speak here. And I want to start with, thank you, Yanis, for the introduction and the title. Now, I should say before starting, but I didn't write this down, 3 things. One is about the collaborators with whom this subject was developed. So I developed it in collaboration primarily with Labros Labru, who is a postdoc at MIT moving to UBC. Also with Jan de Boer, who is a professor at the University of Amsterdam. And also with James Sully, who is, and Sam McCandlish. James is also a postdoc at UBC. And that's the first thing I wanted to say that's not on the slides. The second thing is I haven't written down any references in these notes, but on the last day, I'm going to put up a page with references. Probably if I wrote them down here, nobody would actually copy them, but at the end, maybe they will. And the third thing I wanted to say is that if you are thinking about doing a PhD in the safest country from COVID in the world currently, that is in China, then you are very much welcome to do that. Tsinghua has opened a fast track for foreign students to do their PhDs here, and I would be very happy for good students to apply to do their PhDs with me. So if you know somebody in that position or you yourself are, then please contact me. Okay, now for the subject of the lectures, modular berry phases. So I'm going to start just by talking about berry phases. And I'm pretty sure that the way I will present the subject, and I will spend quite a bit of time on it, there will be, even if you have read a lot about berry phases, you're probably going to see something new here. That's just my guess. So yes, so don't dismiss this. If you have recently studied berry phases, it will probably still be interesting or at least new. Then I will move on to some preliminaries from the ADS CFT correspondence, where we will actually want to apply our toolkit with berry phases. So I'll review necessary facts about ADS CFT for the discussion of modular berry phases. And that's the new thing that I want to introduce. And then I'll talk about applications. So a set of applications that I will definitely cover is, I will tell you that the curvature of ADS spacetime in holography is really a manifestation of these modular berry phases. I will also tell you that in some cases, at least, lengths of curves, not extremal curves, but arbitrary curves, in some cases, are also manifestations or examples of modular berry phases or generalizations of them. And so things that are very practical and necessary and very sort of intrinsic to integral to how we understand the emergence of gravity from a CFT in holography, a lot of the features of that fact of this emergence are really best captured by studying modular berry phases. And that's the thing that I want to convey to you primarily. But if I have time, I will also talk about other applications. One is to holographic complexity and another to quantum computing. I put a maybe there. And these are applications that are still under development. They're not written up in any paper, but I'll talk about them if I have time. Okay, so with that, let me start the discussion of berry phases. So, and I'll start with the derivation. So for talking about berry phases, we need to have the setup is that we imagine there is a time-dependent Hamiltonian. Oh, and I forgot to say one thing. If anyone has questions, please interrupt. I will be very happy to answer questions, and this is meant to be pedagogical, so questions can only help me. Okay, and now for this. For discussion of berry phases, we need a time-dependent Hamiltonian, which I denote here h of t. And I imagine there is some parameter that actually controls what the Hamiltonians could be, which is lambda. And lambda varies with t, and h is defined by a lambda. Now, a typical example is a spin in a magnetic field, which we can just point in different directions. So here is a B field, and here is some spin, which can either point this way or that way, or maybe in some other way. And given the direction of the magnetic field, assuming this mu is positive, the spin would point this way in its ground state. There's also an excited state which points in the opposite direction. If we just move over this B field, then the ground state is going to readjust and point still in the direction which is opposite to the B field. And so by moving or reorienting the magnetic field, we can change where the ground state is pointing. And assuming that the Hamiltonian changes adiabatically slowly, we have some interesting physics that arises from that setup. So in particular, if the system started in the ground state, if it initially points in this direction, then it will remain there in the ground state if we are changing the Hamiltonian, if we're changing this B field arbitrarily slowly. So we can write the ground state of h of lambda. Let's write it using some notation, some psi of lambda. This is going to be our ground state. But this is a ground state with an indefinite phase. I'm not telling you how the phase of psi of lambda is chosen. So psi of lambda could mean what you mean by psi of lambda, or it could mean your psi of lambda multiplied by e to the minus I theta for some arbitrary theta. And I'm just not being specific here about what the phase of psi of lambda is. Those phases, however, will be the key subject of interest in studying Berry phases. So because the system starts in the ground state and it remains in the ground state due to the adiabatic theorem if the Hamiltonian is changing slowly, therefore the state at any time can always be written in this form. It is the psi of lambda plus up to some extra phase which is undetermined right now. This is what we can write down for the state without knowing anything, just by the adiabatic theorem. And I want to also point out here something about the notation. So phi here will represent for me the actual state of the system at the time t, whereas psi is the ground state of the Hamiltonian, but it's the ground state in this unknown phase. Whatever the phase is, psi could be that. Okay, so now, I didn't realize that that's how it would look like. Let me just probably change view to a different view. Is this visible to everybody?
Yeah, that's fine, yes.
Can you, it's good? Okay, yeah. So I was using a full screen view, and full screen view doesn't work that well, it turns out. Okay, so now we're going to take this, what is now our ansatz for the state at a given time t, and we're going to plug it into the Schrödinger equation. So this is what this equation has to be satisfied. Just for simplicity here, I'm going to assume that the ground state energy is actually 0. We can always make that happen by adding a constant to the Hamiltonian. If we didn't do this, there would also be an additional phase, which is the dynamical phase, which is this. But we are not interested in that dynamical phase, which is kind of trivial. So I'm going to ignore it. And the best way to ignore it is just to say that the ground state has 0 energy. So it's not even accumulating it. We are interested in an additional phase, and that additional phase is the interesting one. So if I make this assumption and set h ground state going to 0, then the right-hand side of this equation vanishes right away. And we end up with this equation here. This equation has 2 terms. Remember, our phi is psi, the ground state in an unknown phase, plus the extra phase that makes it right. So I have 2 terms now, one from varying the phase part and one from varying the ground state part. These are the 2 terms here. I'm going to, and we know that these 2 things together combined are going to equal to 0. So we have an equation which allows us to extract gamma dot, the variation of gamma with time. We can extract it by left multiplying both sides by this object, and this operation turns this equation into this equation, which is d gamma dt. That's how gamma, the phase, varies, plus some term equals 0. we can solve this for gamma, or really solve this for d gamma first. And d gamma is this expression, which we can then integrate and get the full gamma, which is the full phase. The object we are integrating to get the phase is called the Berry connection. Really, it is a one form so that we can integrate it along a trajectory to get the full phase. And notice that I didn't even need the lambda of, so first of all, time has already disappeared from this equation. I started talking about a time-dependent Hamiltonian, but the little dt's that are here, they vanished from the equation already. So it doesn't really matter how slowly or how fast time changes, so long as we are still maintaining the validity of the adiabatic theorem for this to go through. I just have some d lambdas, but notice that even the d lambdas can drop out. So it doesn't, this is a statement that it doesn't matter how I parameterize my space of Hamiltonians. This is an object which is intrinsic to the geometry of the trajectory, and it doesn't care about our particular characterization or parameterization of the trajectory with this lambda parameter. So a much nicer way of writing the Berry connection is just to write this. This is what it is. I also want to say, so we don't need lambda to write it. Notice that this Berry connection one form can equally well be written with the opposite sign in this way. So instead of d psi being in the cat, we can have it in the bra. Why is this? Well, it must be true for two reasons. I will tell you two reasons. The first reason is we have psi, we have phi, the physical state, be in this form, remember? And this gamma must be real. Because gamma must be real, therefore, phi d phi has to be imaginary. Why is this? Does it have to be? Okay. Why does it have to be imaginary? Because this object multiplied by I is going to give me a phase, and a phase must be a real thing. So this thing had better be imaginary. Is it imaginary? Well, if I take psi d psi and take its Hermitian conjugate, that just flips the expression. But this is a scalar. The fact that it's a scalar means that Hermitian conjugation is just complex conjugation. But now, this complex conjugation, if this is going to be imaginary, this object must be minus the object written in the opposite way. That's the only way that this will be imaginary. So why is it true that psi d psi is minus d psi psi? Well, that's because I'm taking normalized states. So I have this equation, psi psi equals 1. If I take a variation of it, I see that d psi psi plus psi d psi equals 0. So these things have to have opposite signs. Not only do they have to have opposite signs, because they're Hermitian conjugates of each other, they also have to be imaginary. And so this is how we confirm that this one form, when integrated, will really give me a real phase. This is an imaginary guy, multiplied by I gives me a real phase. I want you to remember this equation, because we'll return to it in a moment, and this is a sort of a key point of the discussion, of all the future discussions. Now, we have gone through a derivation. Normally, I would ask here, are there any questions? It's a little hard to get questions through Zoom, but are there any questions? So we have an equation. First, we have an equation which tells me that this quantity must be imaginary. We have an equation which tells me that if that imaginary quantity multiplied by I is gives me d gamma, a differential of the phase, so that integrating this guy gives me the full phase. So this defines for me a one form, which is the Berry connection one form. We have derived all these facts through a sort of blind application of the Schrödinger equation. So I want to talk about what this means physically. So the statement that I want to put forward is that after we included the Berry phase, our time evolution in some sense becomes simpler. So how does it become simpler? Again, I remind you of our notation. Phi is equal to psi of lambda with some phase. I'm going to imagine that there is no initial phase. So in the beginning, that phase is 0. I can just choose phi equals psi in the beginning this way. And then I want to compute what phi, the physical state, will be differentially farther or later in time. So phi of t plus dt, what is it? So because I'm just going by a little dt to the future, that means that I'm allowed to work to first order in dt. And remember, two things are changing about the state. Our state still satisfies this is written in this fashion. It still has this subject to this ansatz, except that gamma of the initial t is equal to 0. And now I'm going to vary it to first order in t. So varying it to first order in t gives me two terms. One is just the psi alone is changing. This is, I have the old psi plus dt multiplying the appropriate expressions so that we get a dt variation of the state itself. But then I also have that phase, and the phase was initially 0. So e to the phase was equal to 1. Now I have e to some expression which has dt sitting in it. And I wrote out the expression fully. This is the Berry phase that we have picked up after a time dt. And expanding this exponential to first order gives me this expression. Okay. This term here was already expanded to first order. It is this. So I don't expect the audience to necessarily do these manipulations in their head right away, but I wrote them down all in detail. The final outcome after you clean up all the mess is that our phi of t plus dt, so dt later than phi itself, is given by the original psi plus what we would call d psi minus an extra term, which is psi d psi projector acting on d phi. So this means that if I didn't know about Berry phases, I would just go ahead and say, the phase is arbitrary. Let me just say that the state is always the ground state, so it's always going to be given by phi. I changed the Hamiltonian a little bit. Now the state is phi d phi. That's what it is. Without the Berry phase, I would just stop right here. But then I have this extra term. And what is this extra term? It takes d phi, the variation in the state, how the state changed, and it projects it onto the original state. It applies a projector phi phi on it. This means that we have taken the new state without the Berry phase, and we have projected out from the change the piece which points in the direction of phi. So what the Berry phase does for us is that it ensures that the state changes in directions which are orthogonal to itself. If I didn't project this thing out, a piece of d phi is there, which is still proportional to phi. We're just, the Berry phase makes sure that we get rid of that piece. Okay, so here are some sort of emotive ways of rephrasing this. One way is to say the state doesn't speed up or slow down the accumulation of a phase. Do you know why I say this? I say this because of an analogy. Imagine that you have a ball and you are flinging this ball around so that it remains in circular motion. Yes. As we know, there is a centripetal acceleration. If we didn't apply it, the ball would just fly away in a straight line. Yes. So to keep the ball running on a circle, we have to keep applying a centripetal force, and the ball has to feel a centripetal acceleration to stay on course. Yes. But there is an extra, this centripetal acceleration always points orthogonally to the instantaneous velocity of the ball. But there is something else that I can do. In addition to maintaining a constant radius of spinning, I can also make the ball spin faster or slower on the same, but along the same circular trajectory. So I could be going this way, like this, and then I could just go faster and faster. This kind of change would be derived from an acceleration which points parallel and not orthogonally to velocity. The Berry phase is a phase which gets rid of, is such that we are never speeding up or slowing down in the circular direction, which is the direction, which is the rate at which the state acquires a phase. So we are not incurring any acceleration which is parallel to the motion in Hilbert space. We're only changing orthogonally to the state itself. This is the way to think about this. Okay, so that's for this statement. The state changes in directions orthogonal to themselves. It's only true because we have included the Berry phase. Without it, it wouldn't be true. Here's an equivalent statement. An equivalent statement is, suppose that I have this d phi, and I just write it. This is the d phi is the change in the state at time t in the physical state after including the Berry phase. I want to relate the change in the physical state, including the Berry phase, to our arbitrary parameterization. And the way I write it is d psi. But again, I'm projecting out this phi component of d phi. Yes. So this is the Berry phase correction to a naive change in the state. Now, notice that this equation immediately gives me phi d phi equals 0. So if I just put in phi here, you will see that phi d phi is equal to phi d psi minus phi psi phi d phi, and that object vanishes. So the interesting fact is that when I okay, so that's another way of saying it. An interesting fact which is related to this is when I compute the overlap of a state at time t and a state at time t plus dt, it will be given by phi of t plus inner product with itself, and then there is phi d phi term, of course, yes, from this inner product. Our gauge condition is that, or the Berry phase, after the Berry phase, we end up with a situation where phi d phi is equal to 0, which means that this term vanishes. Yes. And so we end up only with phi phi inner product here, but that phi phi inner product, if I have a normalized state, is equal to 1. So the Berry phase, just let's see what this equation is telling us. This equation is really telling us that the Berry phase is the unique phase such that the inner product of the state right now and the state little dt later is going to be real. Any other phase would have given us some non-zero value here, but we already know that this guy is always imaginary. So whatever other phase we could have had, the inner product wouldn't be real. It would be 1 plus something imaginary. It's only the Berry phase that allows this inner product to be 1 and real. Remember that we are working with normalized states. So 1 is the maximum that the inner product of any two vectors can be. So another way of saying it is that the inner product of the state right now and the state little dt later is real and maximal. And this is a condition for what Berry phase does for us. Okay. Otherwise, phi d phi adds an imaginary piece. There is, and then finally, maybe one more perspective on what the Berry phase is. These are perhaps almost indistinguishable, but they all have their own merits. Because phi d phi is equal to minus d phi phi, because these things are imaginary. We talked about it before. So, so if I want to vary the inner product of phi with itself, I know that I get 0. D phi phi is equal to 0 because this object is always 1. I'm always normalized. But it splits up into these two pieces, d phi phi plus phi d phi, which are necessarily of opposite signs. The Berry phase gives me this condition. So the Berry phase is the only phase that I can choose for phi such that not only is the sum equal to 0, but also the terms individually are equal to 0. And so that's another way of thinking about what the Berry phase is doing. I have these oppositely, I have these things which are trivially opposite in magnitude, which look like a variation of the normalization of the state. I'm not actually varying it, so there's 0. But then there are these two terms that work in opposite fashions. I want those terms to not just kill each other off, but actually vanish identically. Okay. And then you might ask, is there a physical reason why I may want to set these terms to 0 individually? What does it matter? And so the answer is that physically, this thing really ensures time reversal symmetry. Why is that? If I take phi d phi, whatever this is, just this term, and I apply time reversal to it, just to that one term, time reversal is really enacted in quantum mechanics by taking Hermitian conjugates. So this would send me, time reversal would take this object to phi d phi Hermitian conjugate. But Hermitian conjugate just means d phi phi, And remember that d phi phi is equal to minus phi d phi. So time reversal takes this guy and multiplies it by an extra minus sign. The only way that we can save ourselves from breaking time reversal is to set this object to 0. Whatever non-zero value it has breaks time reversal. And that's the condition I have. Yes.
But sorry, just like to interrupt, but I guess, I mean, you mean phi here? I'm a little bit confused, like, I mean, between psi and phi. So phi was like the one that you evolved, right? It's the evolved one.
Yeah, so here I was assuming, so I was saying, suppose that I am not including the Berry phase. If I'm not including the Berry phase, then I would have some other phi. I could also vary it. It's also normalized. And then I'm asking, what is the variation? What does it mean to have phi d phi, a variation in an arbitrary state? And the statement is that if we pretended that these arbitrary phis were the physical arbitrary size, were the physical phis along time, then that choice would necessarily break time reversal. Therefore, it would be the wrong choice. That's the logic that I'm trying to put forward. And so from that point of view, Berry imposes, I'm sorry for this, but it meant to write imposes. Berry imposes adiabaticity. It's the statement that if we are really changing the Hamiltonian so slowly that it really stays, the state really stays in the ground state, then it must be doing it in a way that doesn't break time reversal. And if it's not breaking time reversal, it can't be an arbitrary phi, because then this would be acquire a non-zero value. It has to be the Berry phase dressed phi, that because only that one doesn't violate adiabaticity. This is the only choice that doesn't break time reversal invariance. Okay, so this is what I just told you right now was probably a more detailed version, or maybe not, of the kinds of things that you would ordinarily read in a textbook that doesn't focus on Berry phases in particular, but just talks about many things. If you open a very detailed textbook, which specifically talks about geometric phases of all kinds, then you will get a different treatment, and this is the treatment that I'm going to tell you about next. And it's this more robust, more flexible language that will allow us to get a bit further. And in a moment, we will confirm that that language is really doing the same as what the Berry phases are doing. That more general language will be ready for ADS-CFT applications. So this right language is the language of fiber bundles. So what's a bundle? It's basically a geometric object where I have one type of thing which is fibered over another type of thing. So for example, the base could be the space of all possible Hamiltonians, h of lambda. Or it could be the space of all possible ground states, phi of lambda. Okay? These are some of the options. I actually crossed them here because we will want a different type of phase. Physically, we want this base to consist of the things that we actually are controlling. But even though we may be controlling the magnetic field in the case of a spin in a magnetic field, or maybe we're controlling some other parameter in a Hamiltonian, the Hamiltonian is changing, and that is encapsulated by the base directions of this picture. But then there are also the fibers. What are the fibers? The fibers are the things that are arbitrary in our description of the state. So in particular for Berry phases, I want the fibers to be U1s. I want them to be the different phases that the state may have for a given choice of a Hamiltonian. So fibers will be phases, and then the base is going to consist of those things which are physically distinct about different choices of Hamiltonians. It's a little bit of an overkill to say that I want the base to consist of the Hamiltonians themselves. Why is that? If I have a two-level system like a spin, changing the Hamiltonian necessarily changes the ground state, so that's okay. But if I had a three-level system, I could imagine following the ground state and then changing the Hamiltonian only in a way that only affects the second and the first and the second excited state. So it doesn't actually touch the ground state, but this is a variation of the Hamiltonian. So maybe we don't want the base to consist of all possible Hamiltonians, because some of these changes don't have any effect on the Hamiltonian. On the other hand, we really would like something that only is sensitive to what the ground state is doing. On the other hand, we can't choose the base to be just ground states themselves, because they are ambiguous by a phase, and the phases are already here in the included by the fiber directions. And so the base is going to consist of phaseless ground states defined up to a phase. A fancy way of saying it is that this is the projectivized Hilbert space. Another way to say it, which is maybe easier, is that this is the space of projectors onto the ground state. You see this object, phi, cat, bra, projects onto the ground state, and this object doesn't care about phases, because phi cat and phi bra have opposite phases, so they cancel out. So maybe the best way of thinking about what the base consists of is that it consists of all the different projectors onto ground states. Okay, so this is the picture we have. The base here consists of all possible projectors onto ground states, and the fibers consist of all the different phases with which we could dress just this guy, just this phi of lambda. And now, what we do physically is we physically change the Hamiltonian, for example, by changing the direction of the magnetic field. So that corresponds to some trajectory in the base. And then we are asking, is there some effect on the fiber directions? Is there some extra phase that we picked up because of this change in the base? So that's the kind of question we are asking. Now, the way that this question is answered is by introducing something called parallel transport. So what is parallel transport? Parallel transport does this. If I imagine that I started here and with some particular phase for my initial state, then at the next step, I need to choose whether the next state is going to have this phase or this phase or this phase. And only I'm declaring one of these choices to be correct and the other ones would just be wrong. Okay? This correctness in the Berry phase example that we discussed a moment ago was the imposition of the Schrödinger equation. We imposed the Schrödinger equation and it told us that there is a specific phase we must pick. And so it told us that if I'm starting from here, I have to go there, not there, not there. Okay, so this choice of where I go next, given that I started here, is the choice of parallel transport. And the Berry connection or any other connection specifies what the correct choices are. So now, if I already know what the correct choices are, if I have made some choice of the parallel transport condition, like Berry did for us, then I can take this trajectory in the base space and I can lift it to the fiber direction. If I started here, my parallel transport condition would tell me that next I will go here and here and here and here. And then at the end of the day, when I arrive back at my initial point in the base, did I arrive at the same point in the fiber directions? Well, not necessarily. If I did not, then I have incurred what we call a holonomy. This difference between the initial and the final location in the fiber directions after I close the trajectory in the base is called the holonomy of the connection, and the Berry phase is an example of such a holonomy. The mismatch in the fiber directions after parallel transporting by a closed loop in the base, the holonomy of the connection. And the Berry phase is exactly that. This is again a place where I would say, are there any questions? Okay, so there is one more piece maybe of terminology that is useful to introduce here. When I choose to go from this initial point in the total space to either here or there, and I declare that one of these choices is the correct one, the parallel transported one, and the other choices are wrong, they don't do parallel transport, then I am taking the tangent space to this point in the total space, and I'm dividing it into two orthogonally complementary pieces. One is called the vertical space, and the other one is the horizontal space. The vertical space is easy to understand. It's how I am changing my in the fiber directions without moving in the base at all. What's the choice of a horizontal space? It's a choice of what I declare to be orthogonal to these directions. So if I go in this direction, it looks like I have moved a little bit this way, but also I have moved upwards if I happen to go here. And the choice of parallel transport is a choice which tells me which of these possible motions, this one, or that one, we are declaring to be orthogonal to this vertical motion. There is no a priori prescribed way of telling us which one is orthogonal, and we're making that prescription. And making that prescription means choosing a notion of parallel transport. It means choosing a connection. So choosing a connection is a choice of which of these motions, this one or that one or that one, will be called horizontal. If I happen to, once a choice is made, if I happen to make a wrong choice that does not conform to our choice of parallel transport, then we think of this as a coordinate change in the base. Then I have to correct this, and correcting that means adding something that goes just vertically to help with or to fix my wrong choice. This piece which helps is what we typically call the connection when we study general relativity, for example. It's a way in which we can fix some arbitrary choice to make it horizontal. And so what we call a connection in GR or in differential geometry is that vertical motion which has to accompany some arbitrary motion to make it horizontal. Okay. The best way, however, to specify a parallel transport is not by writing down a connection explicitly as an equation. Well, that is very good for different purposes. For example, in GR, that's what we do. In GR, we just say, well, here are the Christoffel symbols. These are the connection terms that we just write down explicitly. But in more abstract applications, when we are not moving vectors in some space, but maybe moving more complicated or more abstract objects, it is much easier to specify what parallel transport is by specifying a rule which tells us what horizontal directions, which directions are horizontal. So specifying parallel transport by specifying these horizontal spaces. And an example of such a specification is this condition which we saw for Berry. It's this phi d phi equals 0. When I write phi d phi equals 0, it's telling me automatically that this would not be this is not a horizontal motion. This is not a horizontal motion because they're not orthogonal to phi itself. It's only in this motion that that d phi is orthogonal to phi itself, and that's what I'm calling parallel transport or a horizontal space. In what we do next, yes.
Sorry. So you said that this is one possible choice, right? Like, I mean, how to specify. So what are other possible choices? Like, I mean, in this case.
Well, so in the Berry case, this equation phi d phi equals 0 is actually only true when I set the Hamiltonian to have 0 eigenvalue on the state. So if I didn't have a 0 eigenvalue on the state, the correct answer here would be phi d phi equals the dynamical phase that I have incurred. And so from that point of view, the different eigenvalues of the Hamiltonian are actually giving me different choices for parallel transport. But this is sort of a trivial.
I see. So it corresponds to the dynamical phase, like to the original eigenvalue of the Hamiltonian that you removed in the beginning.
Yeah, so I removed it here, so that's why I got 0. If I didn't remove it, I would get something else. So there's nothing sacred about 0. It's just removing it makes it a lot easier to, maybe this is another way to say it. So we're really choosing what we mean by orthogonality. See, it looks here like we didn't choose it. Phi d phi was supposed to be 0. This is an orthogonality of something. The point is that if I didn't have the energy eigenvalue equal to 0, then what I call orthogonal would actually mean that I want some specified angle in Hilbert space between these two things, and that angle should be related to that phase. So I'm choosing orthogonality in a much more abstract way than just saying phi d phi equals 0 in general.
Thanks.
So I want to say that mostly we will be solving problems that relate to parallel transport and to different phases in precisely this way. So we will write down some equation such as phi d phi, except these equations will be more complicated in what follows. And we will be saying this equation specifies parallel transport for us. Namely, it tells us which of these arrows is the correct one and which ones are wrong arrows. That's the kind of thing we will be doing. We will not really be writing down connection terms the way we write down Christoffel symbols in GR. This would not be illuminating, and we're just not doing that. We're mostly just writing down what condition sets for us parallel transport. But these are physically and even geometrically equivalent ways of specifying parallel transport. This one is just more robust and easier to understand. Okay, and so this is what I just said. We'll mostly solve problems by specifying horizontal spaces such as this for Berry. And just to make the link with the usual usage of the words connection and how we usually learn gauge theory, I want to make this a little clearer. So normally when we study gauge theory, like in particle physics, we talk about covariant derivatives, right? So a covariant derivative is a combination of a coordinate derivative and something that corrects it, which is the connection term. But the action of this one is not gauge invariant, yes? So in different gauges, we will have different actions here. This is like saying that if I choose one gauge, then d lambda would look like it takes me from here to here, or in some other gauge, d lambda would take me from here to here. But the gauge invariant combination is after I add to it gamma lambda, the corrected object. So we're familiar with this from general relativity, but and we're probably familiar with this from particle physics, where we talk about gauge theories, dynamical gauge theories. But can we relate this to the Berry problem at hand? And so here is how we do it. We say, let's suppose that I have my phi of lambdas, which were these arbitrarily phased ground state of different Hamiltonians h of lambda. And I'm going to vary them. So when I vary them, I just have a d lambda that does that. But remember, this was not gauge invariant, or in other words, this d lambda contains some arbitrariness in it because our states phi were arbitrary. So the way to fix that ambiguity is to subtract something, and subtracting that something is subtracting the projector onto the state phi. And that projector here has the same value as it numerically, the projector of phi on d phi is going to give us a numerical value of this gamma lambda. That's what gamma lambda is. So for Berry, the covariant derivative is d lambda minus d lambda with a projector onto the ground state. And notice that when I use this, okay, notice that d phi, this is the physical change in the state, can be thought of as the covariant derivative acting on an arbitrary phi. Because the covariant derivative has this d piece that gives us d phi, but then we are subtracting the d piece projected onto phi d phi, which is this object. And this object is, so it's by definition a covariant derivative acting on phi. This object is also the variation of the physical phi after we included the Berry phase. So we can think of the variation of the physical state as being the covariant derivative acting on a state in an arbitrary gauge with arbitrary phases. So do these statements make sense or no? So
yes,
I'm hoping that.
Sorry, I have one question, but finish the sentence if you would.
Yeah, so I'm hoping to convey that the extra phase that we have included in our Berry phase discussion that Berry told us about is what Berry told us about is just adding this term, which we usually call gamma lambda in GR and in gauge theories and in particle physics gauge theories, and the variation of the Berry dressed state is really the covariant derivative acting on an arbitrary state.
So the question is like, I mean, you hear this expression for the covariant derivative, right? I mean, you're subtracting this projector. So, but this difference is also a projector itself, right? I mean, so I guess, I mean, it's projection in the orthogonal direction.
I'm subtracting the projected piece. And so what I'm retaining, what capital D is the piece of d phi, which is not parallel to phi itself.
Right.
Orthogonal complement.
Right, but if you factorize the whole thing out, right? I mean, so you write 1 minus the projector times
I could.
its side. That's also a projector, right?
Yeah, I could have written it as 1 minus phi d phi, and then d lambda is acting later.
Right. So and that is projecting, like, I mean, to the orthogonal direction, I guess.
That's projecting to the orthogonal direction. So it's saying if the state is varying, it's only varying in the direction orthogonal to itself. And so this is probably the most succinct way of writing what horizontal spaces have to satisfy. It's the statement that previously we had a statement like this, but a statement like this was for like this very special parallel transported state, phi, yes? Here is a way of writing this which doesn't care about phases. And the statement is take the state with an arbitrary phase and vary it. That's not going to be zero, this inner product. But if you use the covariant derivative, then it will be. And so that defines for me what the covariant derivative is supposed to do. Okay, so this was about the what Berry parallel transport does. There is a thing about Berry connections that makes them interesting, which is that they have curvature. So what is curvature? A curvature is, suppose that I wanted to compute a holonomy for a little parallelogram in the base space, which has infinitesimal, very, very small little legs, and I'm just moving along this parallelogram. So one way that I can write this is I'm moving in some d lambda 1 direction and some d lambda 2 direction. And then I could close it around this way. But another way of saying it is that I'm going to go this way forward, and I'm going to go that way forward and just take the difference. This is equivalent to going all the way around this way. And so what I'm really doing is taking the commutator of the lambda 1 parallel transport and lambda 2 parallel transport with the commutator of these two things. Lambda 1, lambda 2 minus lambda 2, lambda 1 parallel transport. And that mismatch going in one direction or in one order or in the other order and doing parallel transport, this mismatch is the holonomy. But this holonomy we know must be proportional to d lambda 1, d lambda 2. Because the only way in which I can have a mismatch is if lambda 1 and lambda 2 are not parallel to each other. If they were, I would be subtracting things which are well, basically I'm taking an anti-symmetric object in lambda 1 and lambda 2 directions. So it must be proportional to the wedge product of d lambda 1 and d lambda 2, whatever I get here. So if I take this wedge product, d lambda 1, d lambda 2, and factor out something from the holonomy, that something is typically called the curvature. And the way I've written it here, I'm taking parallel transport, which is carried out by the covariant derivative. I'm taking it in two different orders. And so this is the usual way in which we write down curvature. We take the covariant derivative in one direction, covariant derivative in another direction, we take their commutator, and that's what we call curvature. I hope that this picture makes it clear that what the physical significance of this commutator is. We're just taking an infinitesimal loop, the smallest possible loop I can make, and that smallest possible loop looks like a parallelogram, so it has a d lambda 1, d lambda 2 in front of it. So that's what curvature is. And this is an expression for curvature that we have seen repeatedly in the past. We have seen it for the Riemann curvature. We have also seen it for the field strengths of the electromagnetic field and whatnot. But the Berry phases, because they're computed by connections, are not an exception. There is also a curvature which has a more elusive meaning than the curvature of, let's say, the electromagnetic field, which is also important. So what is the meaning of this curvature? Well, one way to state what the meaning of this curvature is for the Berry phase is that if it's zero, then all holonomies are zero for all closed loops. That's just a fact. So, and the reason why that's true is that if the curvature was always zero, then I could make any loop here, and then whatever the space enclosed by my loop, I would cover it by little parallelograms, and each of them has zero curvature, and so these things would add up and give me zero holonomy. On the other hand, it is not true that the curvature is generally zero. So this was just a statement that if it was zero, then the holonomies would be zero. But typically it will not be zero. So for example, what is it for our example of a spin in a magnetic field? So if I have some magnetic field in some direction, what I'm doing is varying it, yes? So if I vary the direction, the space of the sphere, which is the space of all possible directions where B might be pointing, is like my base space, okay? And it turns out that when I compute the curvature for this particular case, the curvature 2 form is proportional to the area 2 form on the sphere. So when I compute the holonomy, I'm actually computing an integral of this curvature enclosed inside. And so the Berry phase is proportional to the area on the sphere that I have enclosed by changing my magnetic field. If I changed my magnetic field in this way, then this little piece of area is how much how much Berry phase my state will have picked up. Okay. So that's about the curvature, and curvature will be an important protagonist in our story later. I see that I have talked for 51 minutes, so we can break here for questions. Yeah, this is a natural stopping point because I'm about to start talking about ADS-CFT. That's probably after the break.
I see. Okay, good. Thank you very much, Bartek, for the nice first lecture. So yes, if there are any questions, please ask them now.
May I have a question? What about torsion? Is it possible to have torsion from the Berry connection? And if possible, what is the physical result of that? Is it possible to have torsion from this Berry connection, from the wave function?
Torsion. Are you talking about you mean torsion as a difference between the gammas in the opposite with some opposite indices?
Yeah.
I don't know.
This is just the immediate question, listening from your general introduction. So I'm just some torsion in my mind.
This is a good question. So basically torsion is the difference between how we parallel transport covariant objects and contravariant objects. So in the Berry phase example, there is not going to be torsion because it's just a U1 phase, and so these U1 phases have to act in opposite ways. Basically, what I'm saying is that if we did, I know. So I'm doing it on the spot. I am improvising an answer, but I think the answer is this: if it turned out, torsion is the difference between how we move covariant and contravariant objects around. Now, the motion of a contravariant object is like the motion of a covariant object in the opposite direction with an extra minus sign sitting there. And so if I had torsion, that would be like saying that I go around this, let's see a good picture here. I go around here in one way and I get some Berry phase, but then I go in the opposite way and I get a different phase, which is not minus the other phase. Yes, if I take a state and I take it around this way, I get some phase. If I take a state and I move it around in the opposite direction, I should get minus that phase. But I wouldn't be getting minus that phase if there was torsion. Now, this tells me that probably the physical significance of torsion is the corrections to adiabaticity, because I only have the same phases, opposite phases when I go one way versus the other way, if the whole thing is reversible, if it's adiabatic. So I think corrections to adiabaticity are going to introduce certain phases which will break time reversal invariance, and which will break the symmetry between these two different directions in which I can sweep the trajectory. And so yes, that's my answer. I think that's true, but I'm not 100% sure. I've never thought about it before.
Okay, thank you for your inspiring answer. Let me think more about your answer. Thank you.
Thanks.
Any more questions?
Okay, with so few questions, I will feel at liberty to talk for 60 minutes instead of 50 minutes in the next lecture. So if you don't want me to talk too much, ask your question now. Let me give a preview of what we're going to talk about next. So in the next, just to fill in the silence and orient you, what we just talked about was very distant from ADS-CFT. This was this introduction of Berry phases in as much detail as I need. I found in the past that Berry phases is something that almost everybody has heard something about, but almost nobody really understands the subject. And so that's why I went through it in this great detail. I hope you didn't find it boring. I'm talking to the audience at large here. But now we're going to switch gears and not talk about these formal things, where I'm going to first talk about the necessary preliminaries from ADS-CFT in general. And then I'll tell you about how these Berry phases apply to the study of modular Hamiltonians. And so that's the goal for the next hour. And like I said, it will turn out that studying Berry phases of modular Hamiltonians is how we discover the curvature of bulk spacetimes in ADS. It is also how we discover, in some cases, not always, let's say lengths of curves in the bulk, and certain other things. So I'll tell you about that.
Okay, good. So maybe if there are no more questions, then we can take like a half an hour break, and then we come back at
all right.
5.
Thank you
So
very
thanks
much,
again.
everyone.
Yeah, thank you very much, Bartek, for the first lecture.